This is a photograph of the surface of Mars. It's high definition, crystal clear, and it's sitting right there on your phone screen. You probably scrolled past it in half a second without thinking twice. But you should think twice, because that image traveled 140 million miles through the most hostile environment known to man just to get to your eyeballs. We tend to think of space exploration as big rockets and roaring engines, fire and smoke. But the unsung hero of space travel isn't the rocket fuel. It's the invisible thread that keeps us connected to our machines once they leave the nest. How exactly does a robot the size of a Mini Cooper sitting in a crater on Mars send a 4K selfie back to Earth? It turns out the process is a lot like trying to have a conversation with someone standing on the other side of a screaming heavy metal concert while using a flashlight. Now, you might be asking, why don't we just use the internet? Well, in a way, we are, but the Wi-Fi in space is agonizingly slow and incredibly complex. It all starts with the language. Whether it's the James Webb Telescope or the Mars Rover, these machines don't speak English and they don't see pictures, they see data. When a satellite snaps a photo, it breaks that image down into a massive grid of pixels. Each pixel is assigned a number representing its color and brightness. Those numbers are then converted into binary code, a seemingly endless string of ones and zeros. This is the same way your computer works, but your computer has the luxury of fiber optic cables. A spacecraft has to rely on radio waves, and this is where things get tricky. Radio waves are a form of light. We can't see them, but they behave just like the light coming from a bulb. And just like a light bulb, the further away you get, the dimmer it looks. This is called the inverse square law. If you double the distance, the signal is only 1/4 as strong. By the time a signal from the Voyager 1 probe, which is currently leaving the solar system, reaches Earth, it is billions of times weaker than the power of a digital watch battery. To make matters worse, space isn't actually quiet. It's full of background noise. The Sun, Jupiter, and even the leftover radiation from the Big Bang are all constantly screaming out radio static. So, our brave little satellite has to transmit that fragile string of ones and zeros through a chaotic storm of cosmic noise. To do this, the satellite uses a transmitter, which is surprisingly weak. The New Horizons probe we talked about earlier, its transmitter runs on about 12 watts of power. That is a dim light bulb in your refrigerator. Yet, it has to shout loud enough to be heard back home. So, if the sender is whispering, the listener needs to have massive ears. Enter the Deep Space Network, or the DSN. This is NASA's secret weapon. It's a collection of absolutely massive antenna dishes stationed in 3 strategic locations around the globe: Goldstone, California, Madrid, Spain, and Canberra, Australia. They are spaced 120 degrees apart, so that as the Earth turns, at least one station always has a direct line of sight to deep space. We never blink. These dishes are feats of engineering. The largest ones are 70 meters wide. That is a satellite dish the size of a football field. They are cooled to temperatures near absolute zero to reduce their own electronic noise, allowing them to catch that faint, ghostly whisper from the void. But catching the signal is only half the battle. You still have to understand it. Remember that string of ones and zeros? Well, cosmic radiation likes to mess with that. Sometimes a 1 gets flipped to a 0 during the trip. If you were downloading a photo on Earth and the data got corrupted, your computer would just ask the server to send it again. But in space, that's not an option. If you're talking to Pluto, it takes light and radio waves about 4.5 hours to get there. So to say, "Hey, can you repeat that?" and get an answer takes 9 hours. We don't have time for that. So, scientists came up with something brilliant called error-correcting code. It's like a complex game of Sudoku. The satellite sends extra bits of data along with the message mathematical clues that tell the computers on Earth how the data should look. If a bit gets flipped by a stray cosmic ray, the computer on Earth runs the math, realizes the mistake, and fixes it automatically without ever asking the probe to repeat itself. However, even with these massive dishes and clever math, the bandwidth is painfully low. When New Horizons flew past Pluto, it gathered so much data that it took over 15 months to download it all. It was transmitting at a speed of about 1 to 2 kilobits per second. That is slower than the dial-up internet your parents used in the 90 seconds. And this creates a bottleneck. We are building better cameras and sensors that collect massive amounts of data, but our radio systems are struggling to keep up. We are trying to suck the ocean through a straw. That is why NASA is currently testing a new technology called optical communications. Instead of radio waves, they are switching to lasers. In 2023, the Psyche mission fired a laser from deep space back to Earth. Because laser light is packed into a much tighter wave than radio, it can carry way more data. It's the difference between dial-up and fiber optics. We're talking about streaming high-definition video from Mars in near real time. But lasers are hard. Aiming a radio beam is like shining a floodlight. You just have to point it in the general direction. Aiming a laser from millions of miles away is like trying to hit a dime with a laser pointer from the Empire State Building while the dime is moving. But they're figuring it out. And it's a good thing they are, because as we prepare to send humans back to the moon and eventually to Mars, we're going to need more than just grainy images. We're going to need a reliable internet connection for the solar system. So, the next time you see a stunning image of a nebula or a rover wheel on dusty red soil, remember the journey that data took. It started as a beam of light, fought its way through the noise of the universe, was caught by a giant metal ear in the desert, and reconstructed by math just so you could double tap it on Instagram. The universe is talking to us. We just had to build really big ears to hear it.